So in this situation, we have a hot piece of lead added to water in a calorimeter. And that calorimeter just keeps heat from escaping into the environment. And eventually, the lead will cool down and heat up the water. This means that the energy lost by the lead, Q1, has to be equal to the energy gained by the water. Since we know that Q1 equals Q2 and Q equals mc delta T, we can also say M1 C1 delta T1 equals M2 C2 delta T2. So let's make a list of what we know. We'll list things according to lead. So we have it M1, 36.0 grams. The initial temperature is 154.5 degrees Celsius. Let's put some information about our water over here. M2 is 100 grams. Its initial temperature is 24.2 degrees Celsius. The final temperature for them both is 25.6 degrees Celsius. So you can find the change in temperature, and you always do final minus initial. 5.6 minus 154.5, and the lead has a negative change in temperature because it goes down in temperature. That means it's losing energy. And the water will have a positive change in temperature. 25.6 minus 24.2. And the water has a 1.4 degrees Celsius change in temperature. You might notice that the lead changes in temperature a lot more than the water. And this is because water has a relatively high specific heat. It's 4.18 joules per grams degrees Celsius. And most metals have less than 1. So now we can rearrange our equation to solve for C1. We divide both sides by M1 T1. So we get C1 equals M2 C2 delta T2 M1 T1. It doesn't matter if you decide the metal or the water is 1. I just picked the lead to be 1 because it was listed first in the problem. So when we plug into this equation, we have M2 C2 times delta T2 divided by M1 times delta T1. I forgot one thing. Don't forget one of these Q's has to be negative because one of the items is gaining energy and one of them is losing energy. So we'll stick our negative sign in here. If you ever have a C come out to be negative, it's because you left out your sign. It's got to be positive. You can see that delta C cancels out. Grams cancel out. And we get the units for C right here. We do 100 times 4.18 times 1.4 divided by 36 times 128.9. And you should get 0.12611. Let's look at our significant figures. 3, 4, 3, 4, 3, and 3. So we're going to round this to have 3 significant figures. We're going to have 0.126 joules per gram degree Celsius. And this specific heat calculation is actually how we can identify unknown metals. I can give you a metal and you can do this experiment with it and you can see which specific heat it matches. So you can see which metal you have. So now we're using this same process to identify an unknown metal like I had just been speaking about. So we know that Q1 equals negative Q2, which also means M1C1 delta T1 equals negative M2C2 delta T2. We've got our metal, which I'm going to make B1, and we've got water. Our mass is 8 grams. The initial temperature is 100 degrees Celsius. We've got 50 grams of water. At 20 degrees Celsius. And afterwards, they both go to 23 degrees Celsius. So our metal changes 23 minus 100, negative 77 degrees. And our water changes positive 3 degrees. We also know the specific heat of water. It's 4.18 joules per gram of degree Celsius. We've already done this on the last problem, so if we rearrange this equation to solve for C1, we divide both sides by M1 and T1. And get the following equation. And we can plug into that. And I like to keep my units because it shows me that I'm doing the right thing when all my units cancel out correctly. 8 grams times. And these two negative signs turn into a positive number. Grams cancel out, degrees Celsius cancels out. And so we do 50 times 4.18 times 3 divided by 8 times 77. And you get 1.01786. When we look for significant figures, we see 2, we see 1, 3, and 1. So when we round this to one significant figure, we have 1 joules per gram per degree Celsius. And then we could look at a list of metals, of known metals, and find the right specific heat. Now, I will say that this specific heat is probably a little bit too inexact. If we wanted to really know what our unknown metal was, we would need to have a better thermometer and take more precise measurements.